this is my Physics 2211 Lab 3 report. For the introduction, we will first go over part 1, which was determining the mass of a black hole using the net force and Newton's second law. In this case, the system was the black hole and orbiting body, and the surroundings were empty space. In part 2, we were using this mass to determine the necessary initial velocity for a vehicle launching off of a planet orbiting that black hole. In this case, the system was the black hole, the ship, and the planet, and again, the surroundings were just empty space. And for the purpose, we were trying to explore the force of gravity on objects in space and explore the effects of the parallel and perpendicular components of the net force on orbiting objects. For the fundamental principles and results, we have Newton's second law, the momentum principle, in a few different forms here in terms of rate of change. And we also have the velocity and position update formulas, which we will later use. We have a couple constants over here, the universal gravitation constant, as well as a couple given variables here. And for the results, we got the mass of the black hole to be about 1 to the 10 to the 32nd power. And the ship's initial velocity was here, and this is the closest distance the ship got to the black hole. For the first glow script model, I should say, we first had to input a couple of values here. We have the universal gravitational constant up here, the mass of the star, the delta t, and the starting time. And down here, we use the momentum principle in a couple different forms to calculate the net forces using our star masses and velocities. In GlowScript 2, the second part, we use the calculated black hole mass, which we found in part 1, which we input right here. And these are the initial velocity values that I tweaked until I got them as close to the black hole as I could without hitting the black hole or getting hit by the planet. And down here we have some force calculations that we did too. For our findings, we found that for the mass of the black hole was, again, about 1.00934 e to the 32nd power. There's possibly some error just using rounded values such as the universal gravitational constant, but I'm fairly confident in the values we got. And here we have the FNet and FNet parallel and perpendicular components of the force here. For our findings in part 2, this again was just found by me tweaking the values until I got as close to the black hole here in the center as I could. The magenta line is the path of the ship. This was the initial velocity imparted, and this is the path of the planet. For the initial velocity, we got negative 0.35 e to the 6, comma 0.85 e to the 6, comma 0. And we got 5.56321 e to the 9 kilometers at the closest point. And again, there was some possible error using rounded values and constants and carrying that black hole mass over into this glow script. For our extensions, the what does it mean question, what does it mean that the net force and its components are different than the rate of change of the momentum principle? Or the momentum and its components, I should say. So while the change in momentum is equal to Fnet, in this case we were unable to actually calculate the net force, so we had to use the change in momentum over time and its components to then calculate the net force and its components. And for the what if we wanted to go into orbit around the black hole question, this was fairly simple. Again, just me tweaking the values until it entered into a stable orbit around the black hole, as you can see here. And for those values, I got negative 0.5 e to the 6 and 0.85 e to the 6. And it finished at 1.26173 e to the 10 meters away from the black hole. This was somewhat arbitrary. It's just some point on this ellipse. Thank you very much.